Yeah, it's a pleasure to introduce our good old friend Ken McLaughlin from Fort Collins, Colorado, but presently in beautiful and sunny Berkeley. And he's going to talk to us about the intuition and asymptotic analysis from two solitons to a continuum limit of solitons. And so the floor is yours, Ken.
Okay, can everybody hear me?
Yep.
Yeah.
So I'm.
Oh, and Ken, it's recorded. Are you fine with the recording?
Yeah. I sent in my I've sold my soul.
We all did.
So of course, the very first thing is to say thanks for inviting me, and my apologies for my slow responses to stuff. That's I have beaten myself up for that, so I apologize. And it's really great to see many of my old friends. Great to see you all, and so thanks for your patience with me. I guess I should try to do this share screen business. Let's see if I can make that work again. Okay, so I'm going to talk about joint work with Manuela Girotti, Bob Jenkins, Tamara Grava, and Alexander Minakov. And some of you have heard aspects of this talk, maybe most of it before, but hopefully there's some cadeau near the end. D'accord? That's the extent of my French for today, with my apologies also for that. Okay, so solitons are fundamental solutions of nonlinear evolution equations, and particularly in integrable nonlinear PDEs, they will possess solutions that are called multi-soliton solutions or many soliton solutions. And so actually the fundamental example for me is not going to be a single soliton solution, but a two soliton solution. So here is an example. This is a plot of the solution of the modified KdV equation, and I've initialized it at time 0. So what you're seeing is the initial data, and now let's see what happens if we try to evolve it forward in time. Let's see. So let me try to pause it here. So both of these peaks are moving. The taller peak is moving with a faster velocity, and it's almost exactly propagating with constant velocities. It's not quite constant, but what I'm going to do when I press play again is put my mouse on top of this second peak, so you can watch what happens when the tall peak interacts with the small peak and overtakes it. Okay, so the crucial thing to watch is what happens as this peak takes over. Okay, so let me press the play button and then put my mouse there. So there we go. Okay. Okay, so you could see, right, that as the tall peak passed over, maybe you could sense that it accelerated faster, and then as it passed over, the smaller peak was shifted back by some small amount. This was visible, yeah? So that's something about these peaks, that these multiple soliton solutions, that they interact with each other. They more or less propagate like independent particles on straight line trajectories until they interact. And sort of after the interaction, they've shifted in physical location, and then they propagate again with kind of fixed velocities. Okay. So that's just a movie of a two soliton solution. And let me see if I connect. Do I get to? Yeah. So this is now just again the same movie, but on the upper right hand corner is just the position of the tall peak as a function of time. Okay. So the horizontal axis is time, and the vertical axis is just the position of the tall peak. And in the lower left hand corner, that's the velocity of the tall peak, and in the lower right hand side is the acceleration. Okay, so I guess we can just watch it evolve, and you can kind of see in this upper right hand picture that when they interact, there's you can detect a shift in the straight line motion, right? Somewhat. You can really see it better in the velocity profile and in the acceleration profile. Okay. So dynamical interaction is happening. That's the I guess that's a punchline. Okay, so those were just plots of solutions. So what am I looking at? So the solution procedure for many integrable PDEs. So integrable PDEs means I'm probably speaking preaching to the choir, right? But so it's integrable. So then there are always sort of lax pairs floating around. That's a harbinger of integrability. And it's the situation that I'm talking about is when the spectral data associated to one member of the lax pair really linearizes the flow. Okay, and one carries out an analysis of the direct spectral transform to try to see key spectral features of the data, and then use that for well, either good or evil, depending upon which side you prefer to be on. But maybe you want to study singular limits of the behavior of solutions under singular limits, or long time behavior. And in order to do so, one typically analyzes the inverse spectral transform, which I try to pose always as a Riemann-Hilbert problem. Okay. So here's two examples in the bottom half of this screen. On the one side is the modified KdV equation and its lax pair, and on the right-hand side over here is the grand parent of them all, the KdV equation and its lax pair. The fundamental first operator of the lax pair is really the time-independent Schrodinger equation. Okay, so its spectral theory is what drives the show. Yeah, so one of the features of this is my second attempt trying this joke. So one of the features of integrability is that it provides a way to really see all of the phenomenon in a very compact way. Everything that was described, one soliton moving through another soliton, and sort of a phase shift that happens, because you can see all of that very specifically, very concretely in a simple formula, which I have taken great pains to produce in this example. And so let us celebrate one of the great features of integrability and look at a piece of information that encapsulates all of this, everything I have described in a single slide. There it is. You can see it, right? It's a X and T, and as clearly initially there's two peaks to the left, and then later on they interact, and then two peaks to the right. Maybe just a moment to celebrate the glory of this incredible formula. Okay. Well, so maybe there's another way to represent it that's better. And so here's another representation of the two soliton solution, which I would like to take a moment to explain. Actually does contain within it a means of understanding the phenomena that I described at the beginning during the movie. Okay. So what I've written here is a Riemann-Hilbert problem, okay, and the quest is to find this M, okay, and this is in the case of the KdV equation. So M is a row vector, a row vector of size 2, and each entry is analytic in the complex plane except for two poles: the pole at K1, which is this place here, and a pole at K2, which is here. And then there are two poles in the lower half plane that are symmetric. Okay, so I start by describing for you a complex variables problem. Find M, which means find M1 and M2. It satisfies these conditions. It's meromorphic in the plane. The entries have poles at K1, at IK1 and IK2, and then at negative IK1 and negative IK2, and the row vector M has this asymptotic at infinity, 1, 1 plus a correction when lambda goes to infinity. And then the last thing is that the residues, there are these, they're called residue conditions. So the residue at IK2 of M is obtained by computing this limit. The residue at IK1 of M is obtained by computing this limit. There are similar residue conditions in the lower half plane. Okay, so that's a problem in complex variables, and you can find the solution explicitly. Okay, and I want to take a moment to go to the board to explain that. So let me try to pause the screen and go to the board for a second. Okay, and that's a good moment to just ask. And if you have any questions, please have at it. So what I'm doing is I'm trying to write down something which has all the properties that I was describing, okay? So it's a row vector. The first entry, it will turn out, the first entry should have a pole in the, at IK2. So, okay. And let's see. Then it should have a pole at negative IK1. So maybe it's minus beta over lambda plus I K1. So that's a guess at the first entry. And alpha and beta are unknowns. And then I go to the second entry. It starts with a 1 because that's the behavior at infinity. And then it's probably minus alpha over lambda plus I K2 and a plus beta over lambda minus I K1. So I don't know, Marco, can you guys read that?
Yes, it's readable.
Okay, so it's a guess, right? Alpha and beta are just constants. They shouldn't depend upon lambda. And if I can determine them so that it satisfies these conditions, then I will have found an M that satisfies this weird looking Riemann-Hilbert problem, okay? So I guess I should go back to sharing screen now. I'll come back to the board in a second if I'm able to do so. We shall see. So you can't really see my board now, but if you now look at just the upper left-hand corner and say, okay, the residue on the right-hand side, if I multiply out this matrix M times this vector, the second entry is just 0. That means that there's no residue at IK2 in the second entry of M, okay? But there is a residue in the first entry, and I compute the residue by doing this multiplication, and I wind up needing M2, the second entry of M, times this quantity here, 2IK2 e to the negative 2xk2 minus 8tk2 cubed, okay? So, and now if I look at this second equation, it says that, okay, at IK1, the first entry of M has no pole because you compute the multiplication on the right-hand side and you get 0. Does everybody see that? Is that okay with everybody? It's a detailed calculation, but it's useful because it sort of shows the structure of what this looks like. And then there are kind of symmetric conditions in the lower half then that I'm not writing down, okay? So what I want to do as a last fun step is to just write down what this residue condition looks like, all right? So let's take the condition at IK2, and I'll show you my screen again. But what you should remember is that I had alpha over a lambda minus IK2, and that means the residue is the unknown alpha. So I'm going to stop sharing again and just write down what the equation looks like. So this is at IK2 of alpha, and then it should be essentially a limit as lambda approaches IK2 of M2. So inside this parentheses, I'm going to put M2. And then it's just multiplied by this quantity, 2IK2 e to the negative. And then I've got to write out what I have, 2IK2 minus 8tk2 cubed. 2ixk2 minus 8tk2 cubed. So inside of here, I have to write M2, which is this, 1 minus alpha over lambda plus I K2 plus beta over lambda minus I K1. So this is the equation that you get by staring at that first residue condition. Is it okay?
Yeah. Right.
Now I'm going to go back to the sharing again. If I'm able to do that a third time in a row, it'd be just amazing. Okay. So what I did is I wrote down the equation for alpha that's determined by this first condition up here. You can do the same thing for the equation for beta that's determined by this term here. Okay. And you get a system of equations, linear equations, and you can solve those equations. Okay. And that is once I do that, once I solve that, then this formula in the lower right-hand corner of my screen gives me the solution of the KdV equation in terms of the first entry of M. Okay. So basically it's alpha. The alpha that I wrote down, well, it's actually alpha plus beta that gives me the first the solution of the KdV equation. I have to differentiate it, but that's how it works. So any questions about that? It's just, I just described the algebras. There's not much intuition. I promise to give some kind of intuition for how you extract asymptotic information. So far, I've just shown you somehow the mechanics. If you can solve this problem, you get the solution, the two soliton solution of the KdV equation. And this is more or less, that's one way to solve it, is to just make a guess and then solve the induced system of linear algebraic equations for alpha and beta, straightforward, okay? And that gives you, actually, that gives you this. Completely nasty, right? So however, how do you extract useful asymptotic information from this representation? Okay, so now I want you to step back and think, okay, this Riemann-Hilbert problem is actually encoding all of the phenomena that Ken celebrated at the beginning of the talk. Okay, how is it doing that? That's why I want to spend a couple of slides explaining how we think about this and how to extract asymptotic information. Okay, so here we are. This is a Riemann-Hilbert problem, a very simple one. There's no jumps. It's just some residue conditions, searching for a meromorphic function. And now I want to assume that time is very large negative. Okay, time is very large negative, and I'm going to assume that x is like near 4k2 squared t. That's actually supposed to be the location of the center of that tall soliton. Okay, so if you use those two scalings and you look at this quantity that I've put an arrow towards, it's order 1. Okay, the two things in the exponent cancel, and it's just some order 1 quantity. Okay, did I do it right? X times k2 is I get 8k2 cubes times t, and a negative 8k2 cubed times t. They cancel. Amazing. Okay, it's not. There's no typos yet. I mean, at least not there. All right. Now, however, look at this. This term is actually exponentially small. Okay, because if I replace x by 4k2 squared times t, and t is very large negative, you get something exponentially decaying in that exponent. So we're in a situation, I've got a meromorphic function, but one of the residue conditions is exponentially small. Probably I can just ignore it. The other residue condition is order 1. So I'm going to, what happens is the intuition is, if you have that situation, one residue condition has a very small residue condition, and the other one is order 1, you can ignore the small one. And when you now solve a simpler problem where there's only one pole, I would make a guess that there's only alpha, and I just ignore the beta business. That can be solved very simply, and what emerges is this formula right here. U looks like 2k2 squared times the sec squared of. So that's a calculation I did not do, and that's what I would encourage, if you're interested, to do. You should, if you do that, you'll see exactly why you get a sec squared potential, which is a 1 soliton solution. Okay. Well, what if I still keep t less than very, very small negative, a very large negative number, but now move x to be the center of the rightmost soliton? Okay. Well, in that case, this entry that I was formerly calling order 1 is actually exponentially small. Okay. And this the entry corresponding to the residue at IK1, that one is actually order 1 now. So now I look at this meromorphic problem, and my intuition says I can ignore the contribution from IK2, but I better pay attention to the contribution from IK1, because one of them is exponentially small and the other one is order 1. So when I do that, I get exactly a set squared potential at centered at the center of the other soliton. Okay, and okay, you can actually make this more precise and write down the error term, and the error terms in each case are exponentially small corrections. Okay, assuming t is large negative. Okay, so all right, that's the picture when t is large and negative, sort of the beginning of that movie, right? There were two peaks and they were moving along. Okay, so now I want to ask what happens if t is large positive. So if t is large positive, they should be shifted in position, and there was some phase shift, some shift in their position, in their locations that I was drawing our attention to. Okay, so if t is very large positive, let's just see what these two terms still in good asymptotic ordering. So if I choose x near 4k2 squared t, this term here is still order 1. That looks pretty good. But however, problem, the other residue, which formerly was negligible, is now exponentially large. Okay, so that looks like, oh crap, now we got a problem, because we would believe there's no contribution from this residue at IK1. However, it's even larger than the residue condition that I've written down at IK2. Is that okay? So the second piece of intuition is like counterintuitive. If you have one residue condition that's much larger than all the other ones, then maybe it's actually negligible. But so in order to see that, what you have to do is a trick. It's like trick number 7 in the collection of Riemann-Hilbert problem artillery, which is to flip the triangularity of the residue conditions. So here's a transformation. M is this row vector that I've started with, and I just take M and multiply by this diagonal matrix. Okay, and if you look at the diagonal matrix, what am I doing? In the 1-1 entry, I have a Blaschke factor. It's got a 0 at IK2, a pole at negative IK2, a 0 at negative IK1, and a pole at IK1. So I'm exchanging. Oh, and then the inverse of that in the 2-2 entry. Okay. So a pole at IK2 and a 0 at negative IK2, and same thing with K1. It's got a 0 at IK1 and a pole at negative IK1. So I'm really, what this does is it exchanges the poles in one entry for poles in the other entry. So I make a global transformation from A to M, and now I ask, oh, maybe this A still can be described in terms of a meromorphic Riemann-Hilbert problem. So I took the liberty of doing that. Okay, I won't go through these calculations, but it looks very much similar to the Riemann-Hilbert problem that I was writing down, the meromorphic problem I was writing down for M. Let me go back so you can compare them. So the triangularity of the residue conditions flips. Okay, so if you see that it goes from lower triangular at IK2 to upper triangular at IK2, and same thing at IK1, the triangularity flips. And if you notice the exponential factors, they change a sign. So here it was e to the negative blah blah blah, here's e to the positive blah blah blah. Okay, so flipping the triangularity has the effect of changing from something that's exponentially growing to exponentially decaying. The other feature that comes out, which you have to do this fun algebraic calculation to see, is this interesting new prefactor, k2 minus k1 over k2 plus k1 squared. I won't explain where that comes from, but you do the algebra and that pops out of the calculation. Okay, so okay, well now let's see what happens if we let t be very large positive. So now this entry, if x is like 4k2 squared t, this exponential is order 1. And because I flipped triangularity, this exponential is again exponentially small. You know, I replace
Sorry, Ken, I have a question. So can you roll back one slide? Right, so how this changes the triangularity if it's diagonal? Maybe it should be off diagonal?
Okay, so let's see. So it works like this. In the initial, so I think it's correct, okay, but it could always be that I'm wrong. So let's check it. So in the initial problem, M, the first entry of M has a pole at IK2, right? So now when I multiply by this,
okay, you're not conjugate. I see. You're just moving the poles, so to speak.
That's right. Yeah, I'm not conjugating. I'm just multiplying on the right. So this first entry, you know, it kills the pole at IK2 in the first entry of M, and the 2,2 entry actually introduces a pole in the second entry of M.
Okay. Yeah.
Okay. Thanks, Marco. I forget which number I gave. I think that's trick number 7. Okay. All right. So, so because of the flipping of the triangularity, this entry is now exponentially small if t is large positive and x is near 4k2 squared t. And then you can ignore, it's back to the old intuition. I can now ignore the contribution from IK1. And you wind up seeing that if x is near k2 squared t, this is the asymptotic description. It's a single soliton, but check it out. The center of the soliton has now been shifted by this amount, which is independent of t. And if I focus near k1 squared t, 4 times k1 squared t, then I get the soliton corresponding to IK1, except that its center has also been shifted. Now, if you look carefully, it turns out this soliton at the top, its center has been shifted to the right, and the soliton, the smaller soliton, its center has been shifted to the left. Okay, so in that sense, this Riemann-Hilbert problem allows one to extract the intuition from, at least to see the phenomena that I was describing at the beginning of the talk. Okay. And it goes like that. You try to ignore things that are exponentially small in favor of things that are order 1. And when things are exponentially large, you really just don't know what the dominant contribution is. That's the true intuition. You have to do some kind of trickery to put yourself in a situation where there's a controlled factor and then there's exponentially small corrections you want to ignore. Okay. Comments or questions? Let me see how we doing time-wise. Still okay, right, Marco?
25 minutes roughly.
I have 45 minutes left. No, you
25.
25.
Roughly.
Okay.
Roughly.
Well, I'll have to go a little faster. Okay. So that's the case of 2 solitons. And so now you can ask, oh, I wonder if there is a similar beautiful representation that encapsulates all of the possible phenomena for an n soliton solution. And so I think it's a glorious moment in the talk to celebrate this picture. Okay, so here is a meromorphic Riemann-Hilbert problem for an unknown M, and it has poles. In this time I've chosen it a little bit different. It's got poles in the first entry at all of these locations in the upper half plane, and poles in the second entry at all of these locations in the lower half plane. And the residue conditions are given as described on this slide. Okay. The M still goes to 1, 1 as lambda goes to infinity. It obeys a symmetry. And if I can find an M that satisfies this, then the solution to the KdV equation is obtained in this usual way. Okay, so okay, so that is a way to represent an n soliton solution, and we want to use it. We want to use this sort of for some additional fun calculations in the time that's remaining. Okay. And this is the same picture, but not for the KdV, but for the modified KdV case. It's a slightly different equation on the upper left-hand corner of the screen. And the main difference in terms of the analysis is that we're now looking for a 2x2 matrix instead of a row vector. That makes life a lot easier. Okay. Okay, so let me keep moving. So now some fun background history. Okay, so back in 1971, right when this kind of the discovery of integrable nonlinear PDEs was being made, Zakarov considered, for the case of the KdV equation, the interaction of a dilute gas of solitons. And so his idea was that solitons with different velocities, you could have many of them, and they kind of they interact like pairwise only. Okay, and when they do so, they pass through each other, they absorb these phase shifts, and they emerge after that interaction with slightly shifted positions. And so his fundamental example was exactly the one that we just did. Prepare two solitons that look like I've written here in the middle of the screen. So eta 1 is the K1 from my calculations. Eta 2 is the K2 from my calculations. And he's got a 12 there because he normalized the equation differently. And when t goes to negative infinity, what you have is these two solitons. And when t goes to positive infinity, they emerge with a phase shift, just like we calculated together. Okay. Then he says, well, let's imagine that we have a dilute gas of solitons that are described in some gaseous sense with a density that corresponds to a distribution of their velocities, but they're very dilute. Okay, now they interact with each other by like sloshing about, but then he also says, let's put a tagged soliton, a tracer soliton amongst this gas and push it through the system and watch how it evolves. Now, because it's interacting with many solitons, as it passes through this gas, it absorbs shifts in the soliton velocity. Okay, and then one of the contributions of his paper is this equation for the velocity of the tracer soliton. It's no longer constant, but there's a formula for it which is written on the screen there. Okay, and the density F evolves and solves this kind of continuity equation for the density. Okay.
Could I interrupt for a moment?
John, great. Go ahead.
So I'm just a little bit confused. So up till now, you've been talking about exact solutions to a certain nonlinear equation, and it had particle-like properties.
Yeah.
And when you talk about the n-particle solution, same thing. It's got particle-like. It's still an exact solution of a nonlinear evolution equation. But now you're talking about a gas. Now, to me, a gas is something in statistical mechanics, and I don't understand where the jump is made.
Yeah, I completely agree with this complaint, John. And so if you go and you read this paper from 71 very carefully, the word randomness is never there. But of course, it is in my opinion, it's in Zakarov's like psyche as he's doing this. He's imagining that he has some strange configuration where there's an infinite number of poles, and there's some small amount of randomness in them, but the locations of the solitons are spread about. Okay, so it's something imprecise. But he imagines, so it's really that vague. He imagines that you have a soliton propagating through and picking up little kicks every time it goes through and encounters one of this member of the gas. Okay, and
is
then
he still talking about an exact solution of the KdV or the modified KdV equation?
I would say no. He's talking about some compound solution that is obtained by taking a limit of solitons. At the time, that technology didn't exist. Okay, but wait, there's more. I have exact examples of this in about 3 slides. Okay, John.
Okay.
But I just want to say I completely agree. It's not exactly clear what precise solitonic solutions were being postulated in this 1971 paper. I think it was like the idea that it should be some random configuration of solitons. Okay, and this equation, it was initially written down, I think, under the assumption of some statistical mechanical interaction of a gas with a tracer with a random gas of solitons. So bear with me, John. I have a one quick slide which sort of gives intuition behind where this weird looking equation might come from. So this collection of lines, the blue lines are like members of some gas of solitons, a dilute gas of slow solitons. So I think of it as being a packet of solitons that are evolving. Maybe they're not interacting with each other yet because they're still far apart. And then there's the black line, which is sort of the position of a fast-moving soliton that's blasting through this collection of solitons. Each time the black line crosses a blue line, it picks up a kick, picks up a little velocity, okay? And these blue lines, maybe they're described by a density, okay? And now in a small time window, okay, it's delta t, it's not clear what that means, but let's say it's not so long and not so short, so that you do encounter a large number of these blue solitons in that time window. The total accumulated shift is just adding up the pairwise shifts. So I wrote that down. That's like a sum of pairwise shifts. I can approximate that by some kind of a sum over values of eta times the number of solitons whose velocity is connected to the value eta. Okay, and then I can like throw in replace the number of solitons by a density calculation. It says, oh, that's actually how many solitons you've encountered, using the fact that there's some strange density out there. Okay, and this then looks like an integral, and that's where that's the best I can come up with as a back of the envelope explanation for where this formula for the evolving soliton velocity comes from. Okay,
but should we think of this still as somehow showing the dynamics of the support of the bumps in an exact solution to KdV?
So yes, but not from what I've described. From what I've described as sort of a hand wavy back of the envelope, like let's see how, if you encounter some non-uniform configuration of solitons, how that affects the velocity of this tracer. Okay, but let me come back to that, John. I promise to come back to exactly what you're asking about. Okay.
Okay.
It's like it's as though you're a plant in the talk asking the right questions. Okay, so much later, Gennady considered the question, well, what happens how would I model things, again, still in this sort of random situation, how would I model things if the gas was not dilute? And then after he extracted this integral equation, which, you know, as opposed to the previous equation at the bottom of this screen, that's a formula for the velocity, right? The velocity doesn't appear on the right-hand side. It's just a formula. This is an equation where S is the velocity of the tracer, and it appears on the right-hand side. So this equation somehow is supposed to determine the velocity, and it couples the velocity to this kinetic equation. Okay, so that's the extent of kind of a background of very interesting physically motivated calculations that have to do with the dynamics of a soliton interacting with a gas. And I want to skip this in the interest of time so I can make sure to get to John's question. So this is the first example where I want to sort of explain. John's asking, in what sense can I think of many, many solitons as having a collective motion that I could describe by something other than a bunch of individual solitons? I interpret that as one of the questions that John is asking about, okay? So imagine that now, instead of having n solitons where capital N is fixed, that I say on this interval here, this vertical line, I'm going to pack in n poles in my meromorphic Riemann-Hilbert problem and let n go to infinity. okay? At each pole, I have a residue condition that looks like this. And then in the lower half plane, I have a residue condition that is also described here, okay? And the function theta is, I don't know if it's on the screen, I can't see because, yeah, it's just exactly that ik cubed t and plus a 2ikx, okay? So what happens if you let the number of poles go to infinity with all the scalings that I have here? So chi j is going to be a nice discretization of a smooth function. So one question you can ask is, does that limit exist? And for what values of x and t does that limit exist? The short answer is, if x is in a bounded set, the potential that's an n soliton potential converges to a very regular looking function of x and t, which for sort of order 1 values of t is some oscillating function that decays in one direction as though there are no solitons there, but it oscillates all the way out to infinity. And as you go out to infinity, it starts to look like an elliptic wave, what they call a conoidal wave in our field, okay? So in terms of the question that maybe John raised, if you let the number of poles go to infinity in this way, as described on this screen, what you see is sort of a limit in which there's an oscillatory function, which is actually an infinite number of solitons conspiring to give you a regular kind of slowly varying wave solution. I'll show you a picture of that in a second, okay? So this is the Riemann-Hilbert problem that emerges in the limit. There's no longer poles. It's just a jump relationship across the axis in the upper half plane and across the little contour in the lower half plane. Okay, and this is now a Riemann-Hilbert problem which generates solutions of the KdV equation that have this interesting feature. They're kind of going to zero in one direction, but they're oscillatory all the way off to infinity in the other direction, and the oscillations are described in using elliptic function theory, so conoidal waves of genus 1. And as time evolves, the evolution of the solution is under control, but when you do long time asymptotics, you see kind of a modulated elliptic wave theory going on. Those are buzzwords. And I won't be able to explain all of the buzzwords.
Just step in for a second. So I'm sure you're going to answer the question eventually, but what I'm seeing now, I mean, it's very nice, and I guess it's fairly well known, is that if you take a continuum limit of a sum of poles, you get a cut.
Yeah.
Or two cuts in this case it is. But you're still talking about exact solutions of the same equation.
This is an exact, so this represents an exact solution. It's more complicated. It's not a soliton, but yeah.
Right. But I thought it's still this question of where's the statistical mechanics coming in, because somehow there has to be something other than an exact solution where each of the individual solitons has its dynamics, but we're doing some kind of statistical analysis of their interactions. And that's what I don't understand. That does not correspond, I presume, to any exact solution.
So it's a real surprise that in this example, it's completely correct to say that this is not a statistical ensemble. This is an exact solution, a very regular solution. I call it a regular gas because it's achieved by a limit of n solitons, but there's no randomness, there's no fluctuations. It's just a pure, very regular gas. Okay, and so I go to the next screen because I want to show you. This is a plot of the solution at large time. Okay, and as John is saying, it's a very regular looking object. In this direction, as you go off to plus infinity for this particular solution is just zero. You see that the quiescent region is just zero. And then there's this modulated conoidal wave region, very regular oscillations, and then you get as x goes off to negative infinity, the modulations stop, and it's a fixed conoidal wave. We call that elliptic wave. Okay, and okay, I want to point this out. So the dynamics are driven by the calculation of a g function, which, if you're in Riemann-Hilbert analysis, if you're playing if you're playing, you know, the buzzword bingo, you're thinking, when is Ken going to say the word G function? G function is now there. And the dynamics are driven by this function. And so I'll just say, without, you know, this is like the regions of exponential growth and decay. And so sometimes you need a G function, sometimes you don't. When you do need a G function, it's represented as a log transform. And there are these standard variational equations that emerge that determine the function G. Okay. And so I've just written down kind of the summary of step one of the Riemann-Hilbert analysis in this case. It is to determine the function G, which is the same thing as determining the density rho. So rho is kind of determines the subset of the solitonic region that drives the behavior of the solution. Okay. So here's a fact, and that's where I want to, that's where I can answer John's question. If I take this function rho, I can produce a velocity by just saying, choose x and t, so that as t evolves, the value of the density rho is constant. So that gives me some trajectory, x as a function of t, and it gives me a velocity by just computing, right, the derivative, you know, method of characteristics. Negative rho t over rho x is a velocity for that point. It solves this exact kinetic equation. So even though there's no randomness, even though there's no statistics in this, the gas of solitons itself has the property that there's an internal velocity profile which satisfies this very same kinetic equation. So John, that's like, I think I think of it as strong evidence that this kinetic equation is actually real, because, you know, this is an example where you can compute everything and it's explicit. This velocity must solve this equation. Strange thing is that we don't use that. We derive the velocity directly and then just check kind of for fun. Oh, let's see if it does solve this equation. And yep, sure enough, it does. We don't need that fact for anything. Okay. So, but I would suggest, or I'd like to invite us all to say, this means that even though it's extremely regular, even though there's no statistics, no randomness, this solution, this exact solution that I've described here on this page, this exact solution still is a soliton gas, because there's a velocity profile that satisfies the kinetic equations of a solitonic gas. So a moment of celebration, a silent cheer, if you will. Soliton gas confirmed. Okay, so that's step one. Now what we want to do, we want to introduce a tracer soliton to see how it interacts with this gas of solitons. So that's like this Riemann-Hilbert problem. This Riemann-Hilbert problem that I've got on the screen now represents a single pole at I kappa naught interacting with this very explicit, regular, precise solution of the KdV equation. So this thing that I've got here is a new solution that is a gas and a single tracer kind of dancing along with the gas. Okay.
I'm sorry, I'm going to say one more comment and I really promise not to say anymore.
Don't worry, it's fun.
So is there, okay, when I look at this spectrum, I see, okay, there's a cut and there are poles. And I ask myself, we know that solitons can be added to given solutions by applying a Becklin-Darboux transformation, which adds poles. Is that what you're looking at?
Yeah, you can interpret it that way. That's not what we do because you know, I want to, Becklin transformations are somehow too algebraic for me. I want to use only complex analysis. But yes, that's you can exactly either add poles or remove poles by exactly the construction you're describing. Sure. Okay.
In terms of spectral data,
yeah,
you have your lax operator and you have its spectrum.
Yes.
And there can be a continuous part, and then you can change, you can add some bound states. And
Yeah.
that's what would correspond to a soliton.
That's right. Yeah. So let me show you the next picture. So enjoy this, folks. So I can carefully construct that residue condition up there and the jump condition so that this is the initial data, okay? The distance between the soliton and the gas is a large parameter, okay? Let's call it L. So that's a very large parameter. Now I'm gonna let this, so okay, you can see there's a modulated elliptic region, there's an elliptic wave region, and then there's a soliton, and it's gonna take a few moments. Okay, am I over time?
No.
No, you have still 5-10 minutes.
Okay, I'm sure William is thinking, no, Marco, much less than that.
No, that sounds right.
Okay, well, I'm almost done. So now that little interlude has taken place, we're about to see the soliton interact with the gas. And here it goes. So it's really a dynamic evolution, right? As John says rightfully, this gas is a pretty regular gas. Okay, it's actually, he might object to me calling it a gas, but I still do so because it's evolving and it's got a kinetic equation for its velocity. And you can see there's quite a dance. I didn't say dance, I said dance because that sounded better, right? Okay, with my apologies for that, but okay, so now I guess I should pause this and just say, can I pause it? Yeah, there's the pause. I should just say that this region here, there's a modulated elliptic wave region and elliptic wave region. Those constitute a limit of an infinite number of solitons. So maybe there's like, I don't know, 100 solitons that conspire to give you this period from here to here. Who knows, right? So it's like, this is already in a limit. Each peak looks like a soliton, but it's actually a more regular accumulation of solitons. So you remember I had a plot at the beginning of the peak location. This is again the plot of the soliton peak location on the upper left. The middle is I sort of subtracted off the vacuum velocity to see that there are oscillations as the soliton interacts with the gas. And then this is actually a plot after having subtracted off that vacuum location, the velocity, okay? So what you see as T is very large is that really the velocity is oscillating quite rapidly. And this velocity of the tracer is actually an average over those oscillations. Okay, it's very regular, but nonetheless, what you're seeing is that the tracer's velocity is increasing and it's being averaged over this this background wave. Okay, so this is one slide because the other buzzword people look for when they play buzzword bingo is opening of the lens.
Open the lens.
Thank you, Marco. I should have allowed Marco to announce that. There it is. So this is just to say, okay, one can carry out the Riemann-Hilbert analysis. It's straightforward. There's no wrinkles to this, really. And then the only step in the analysis that affects the residue condition, see, the lenses are all being opened away from this IK2, which is up above everything. So the only thing that actually is affecting the residue condition is this the G function, and okay, there's some lower order correction to that. And so that's the residue condition at the bottom. Now, remember the intuition. The intuition was if the residue condition is order 1 and everything else is either order 1 or small, then I can probably compute and the residue condition will matter. But if the residue condition is exponentially small and everything else is order 1, I should be able to ignore the residue condition. So that lets you sort of search in physical space, identify the value of X when T is large, where the residue condition actually is important. And that tells you the center of the soliton. Okay, so it's like the same intuition I started with. Try to figure out when this residue condition matters. Okay, that intuition tells us where the location of the soliton is. And so there it is, the residue condition at the top of the screen. Okay, and so this is the intuition. Small residue conditions are negligible, large ones are also negligible. So you can isolate this by refining the intuition. You can isolate the soliton peak. And so the average velocity is obtained by basically setting this phase function that appears in the residue condition equal to a constant. and then taking partial derivatives with respect to x and t, and that gives you an explicit formula for the velocity of the tracer. And I don't have a plot to show you that, but it's spot on. Okay, this is the averaged soliton velocity, and it actually also satisfies the kinetic equation for the tracer velocity. Even though it's all very regular, very precise solutions, it still satisfies the tracer equation. Okay, so I think of it as like a very regular, organized gas of solitons sloshing about, and a tracer passing through them. And it's a rigorous analysis that shows that you can compute the velocity, and you can show that the velocity solves this equation. But again, we don't actually need this equation because we have very precise information about the soliton itself. Okay, and that's the end. So thanks for listening. Hope that was okay.
Thanks, Ken.
Thank you.
That's we are watching this beautiful movie. What will happen now? So let me ask the audience if there are questions or comments. Ooh, look at that.
I'll stop it there. How about that? That's a good place. A little further. There. Yeah.
It's okay. Yeah. So actually, I let me ask, since maybe other people will think of something, but I have now, in the spirit of what John was asking, right? Now, can you, if you had to kind of dream and imagine that you can now solve the problem with some kind of randomness injected. So where would be you would inject it in, probably in the soliton gas, right? In the data that goes on the, but what kind have you thought about, for example, what kind of regularity, can you just take some kind of, because in order to do some kind of, for example, white noise, right? You could try to think of putting some white noise on this. Then you would have to show that you can solve the Riemann-Hilbert problem when this jump has, in some Sobolev class, I don't know, is there something that you are thinking about?
Yeah, that's I mean, yeah, it's a real challenge, but let me, I draw a picture if okay, yeah. My apologies for taking more time, but I draw a picture, okay? So let's say that's the x-axis, and then t is going this way. So there are computational experiments where people start solitons. Like, I'm going to draw little dots for where you put solitons. Okay, very regularly spaced. So not sort of a continuum limit, but just a large number of them. Each one has a random speed.
Mm-hmm.
Okay, so I'm going to try to draw random speeds. Maybe this one goes like this. This one goes like this. This one goes like that. Maybe that one goes like that. And maybe this one is like very, very like that. Okay. So, okay. And so how do you describe the interactions after a long time? So it's like, to leading order, it should be just the statistics of lines, statistics of crossings of lines. And apparently, I didn't know this, but there are problems where people have studied this. I think they're called oh crap, what's it called? I think solid rod problems. But of course, every time the two lines cross, there's this logarithmic exchange of particle positions, and that has to be kind of accumulated and then sample averaged. And so that's like a totally open direction. How do you compute statistics? The place where I would imagine is something is doable. It hasn't been done, but it's doable. Is you look for the extreme, like where is the boundary between quiescent behavior and solitonic behavior? Try to describe
the fluctuation of the largest random particle, right?
Right, right. Things like that. Sort of interpreting that, translating it into a solitonic case, I think is doable. But so that's something we're trying. We'd love other people to join in and help with that. Of course, probably other. I mean, there are other folks working on this, Gennady and Alexander Tovbis, and a crew around them, and they're considering a different setting entirely. It's not solitons. It's like periodic theory. And I don't want to speculate. I don't want to try to describe their work because I'll get it wrong. Okay, but this is sort of the kind of area where Marco, I think what you're describing would be first things to try, and right now it's wide open.
Okay. Mm-hmm. All right.
Just a shot in the dark, but is there, if you want to introduce randomness, so is there any sense to looking for a stochastic version of the KdV equation or of the associated Lax equation?
That's been a challenge to find it. So for sure, there are versions of stochastically driven PDEs. The analysis of those is completely different. It's going to be based on like the use of probability theory and probably harmonic analysis, but not integrability. And the stochastic Lax operator, that's another awesome thing to try do. It's just that what you need to study the evolution of the PDE is such detailed information that it's hard to get it from a stochastically sampled Lax operator. You need like the eigenvalues, the distance between them, and the norming constants, and that's very hard to get statistical information about. There are examples like the total lattice. There are examples where you can set that up and actually compute the induced distribution on the eigenvalues and on the norming constants. But even there, evaluating the statistics of the flow has not really been done ever.
Right, and it's not a randomness in the equation itself. It's a randomness in the initial data.
That's right. Yeah. Good point. Yeah. That's right. It's only seeding the randomness in the initial data, as opposed to changing the equation itself.
Yeah, the closest thing that comes to mind is this work of Castell, where they studied the KdV equation with the white noise initial data on the circle.
Yeah.
And then the surprise was that the KdV equation preserves white noise, even if it's a non-linear evolution, right? But I think there is also something on the line, not on the circle, but I may be wrong.
I mean, there are PDE results that say that there exists an invariant measure for, I forget which of the integrable PDEs, but there exists an invariant measure, but those don't use integrability.
Right, they don't. Yeah. Okay, so let me ask if there are questions, other questions from participants.
Well, I had a quick question. So you consider a uniform gas of solitons, right?
Yeah.
By the limit you took. But what if you perturb that and induce some non-uniformity that's small compared to the overall density, or is that something that?
So that's probably doable. So I think what you're talking about is maybe that this where the poles are accumulating, if I introduce a density there, so it's not uniform, but like so that's that sort of can be absorbed into this Riemann-Hilbert problem that I wrote down sometimes. Okay, but if you change it dramatically so that maybe the density of poles goes to zero somewhere and then starts to emerge again, then the phenomena is very different. And I don't know what happens there. I would guess that you have to describe it with a more complicated, maybe it's a genus 2 conoidal wave, a genus 2 solution of some elliptic function theory problem, but you can certainly change things dramatically by changing the density of the eigenvalues. And only in the simplest case, if the density is positive, but it sort of deforms a little bit as you go up, that's manageable. But if once you start to allow for a gap or allow for a region where the density gets very small, the phenomena changes, and that hasn't been calculated yet. Actually, maybe Patrick Nabulek computed one example of that, but other than that, it's open.
Okay, thank you.
Thanks, everybody.
So, well, you know that, okay, there are viruses and there are computer viruses, but I doubt that you can catch them, William, from a Zoom session.
No, but he's American, so I don't know. I mean, it's kind of dangerous.
Oh, okay, that's true. Right.
Yeah.
Yeah, I noticed at which point in my talk it went badly, and then William put on the mask.
That's right. It was too
Got to
mathematical.
protect yourself.
As a physicist, I have to keep my integrity.
Yes. Yes.
So maybe one last quick question, getting back from the sublime to the ridiculous. When you have, it's still this exact solution. I still see this as a conoidal plus a soliton.
Yeah.
But just looking at your graphs, I noticed that as the soliton passed through this sort of army of solitons, ranged up like a Roman army in regular order, the height of the first part of the oscillation seemed to have dropped down. Eventually it became the same, but it started out as quite suddenly at a higher point, and then after the marauding soliton went through, it dropped down. Am I mistaken, or did that really happen?
So I'm running it again. It'll take about an hour for the soliton to get there, but just sit tight.
Yeah, but like it comes up rather suddenly and then is very steady, right?
So I'll try to pause it.
Let's see what happens after it passes through.
I mean,
Maybe
you're
I'm just
now going to
pleased.
see some plotter error, okay?
Let's see.
Is that what you mean, John?
No, keep going, keep going. After it's gone through, it seems that the region over which it's rising has extended into a longer region.
Oh, that's true. Right.
Right? So that
It's
must
actually,
mean that
it seems to be kind of,
some energy has been transferred
So
from the Roman army of solitons to the single marauder. Isn't that true? If
Yeah,
you just look at the energy square, I don't know, the derivative squared does the energy or something.
Yeah, that's a calculation. Yeah, I haven't done that calculation, but are you talking about the velocity of this tracer, or what are you talking about?
No,
the question is,
the ones
this is
left
actually
behind.
a plot of the solution. So
Yes.
how should one look at the energy? It's not exactly the amplitude squared. It's some combination of amplitude squared and derivative squared. But there is something which indicates the energy, right? There's some energy density there. And that seems to have transferred to some extent from the sort of quasi-periodic solution to the lone raider.
So wait a minute. I got to get a John interpreter. Marco, what's John saying?
So I think that the first few peaks, right after behind the tracer,
Yeah.
they after the tracer passes over them, they are getting lower, and they are kind of more
look at
spaced.
when it's on the left.
Yeah.
Look at how long
Yeah.
it takes to rise to a steady position, and look at how long it takes after it's on the right. It's longer. It's about twice as long.
Yeah. Okay, I see. Let me zoom forward.
In fact, when it's very far away, it's instantaneous. And now there's a sort of, you could do a sort of average of the part
Okay.
rising,
Okay.
right?
So-
And that if you made a sort of average where you took the
Yeah.
oscillations and averaged them out, you would have what started out like a step function turning into a sort of gradually rising curve, which eventually stabilizes.
So
I guess that mathematically, what John is asking is, what is the behavior of the bulk of this oscillation for large t?
Yeah, right.
After the tracer has gone over them, right?
So here's what I think is, this might answer the question, John, is like, can you see my arrow over here?
Yeah.
Yes.
So in that region, the background wave is what's called a modulated genus 1 elliptic wave. So it's slowly varying. You know, basically it goes from having an infinite period to some fixed period over here. In this region where the solution, it's rising up, that's a region where it's really a modulating wave. And over here, it's a periodic wave. It's actually an elliptic wave with no modulation whatsoever. And it's a soliton sort of passing through a fixed parameter elliptic wave. So what you're seeing when the soliton is interacting with this elliptic wave is that it's still deforming, and it keeps deforming. That region keeps deforming. Okay, and so the long-time asymptotics has got this sort of picture. There's an exponentially small region, there's a modulated region, and then there's the fixed elliptic wave region, and there are phase transitions between them that haven't been analyzed. Okay, so that might explain, if one carefully considers the behavior of this elliptic wave in the modulated region, maybe one can identify that phenomena. We haven't done that. Okay.
Mm-hmm. Okay. All right. Okay, Ken. So
now I'm really upset, William. He's got his helmet on.
Well, it is almost 5 p.m. here. We're not.
You got the protection, right? Step out with the
everything.
protection.
Yeah, this last part was bad. I mean, I put a helmet on.
Good.
All right. Okay. So let's thank the
Solitons
speaker.
hurt.
Thanks, everybody. It's always excellent hanging out with the Montreal crew. I really enjoy that.